Esquentando lá. Acho que o momento mais tenso foi quando caiu um míssil da Rússia no sul da Polônia. Tentando saber o que o governo ia fazer.
Olá, boa tarde a todos. Vamos dar início ao seminário de hoje. Desculpem o atraso, como nós estamos em obras, nós temos que acomodar todos os seminários do Instituto e isso possivelmente vai acontecer novamente. Então, hoje a gente recebe o André Rodrigo da Silva, que por um pequeno momento passou pelo Instituto, mas ele está atualmente no Nicolaus Copernicus Astronomical Center of Polish Academy of Sciences, trabalhando com o Rodolfo, que também foi aluno aqui, e o André fez a master dele, tem título de mestre em radiometria
ambiental.
Obrigada. Ambiental, que ele fez isso no IPEM, e também tem o teaching degree em ciências físicas, que ele obteve pela Unifesp. E ele também começou aqui no IAG, mas aí ele desistiu e resolveu, em 2019, se mudar para a Polônia e lá fazer seu doutorado. É isso, né? E hoje ele vai falar sobre populações estelares que contêm estrelas pobres em metal na Via Láctea, especialmente sobre o processo R e os follow-ups espectroscópicos que nos permitem obter informações a respeito disso. Então, muito obrigada, bem-vindo.
Good afternoon, everyone. I'm going to talk about metal-poor stellar populations in the Milky Way, but focusing on the R process and its implications. So, but first, what are metal-poor stars? Metal-poor stars are stars that have metallicity below -1 dex. They are generally old, and because they are old, they preserve on their atmospheres the chemical signatures and on their dynamics the progenitor dynamics. And because they are metal poor, they are enriched by a few nucleosynthetic events only. All of this to tell you that there is this field of astronomy called galactic archaeology, and what galactic archaeology tries to do is to rebuild the formation history of the Milky Way. So, as it is about the Milky Way, just to recap, the Milky Way is subdivided in the bulge, the disk, and the stellar halo. Most metal stars are located on the star, and it's going to be the main focus of the talk today. Metal poor stars can be accretion relics from an early time of the Milky Way. Thanks to Gaia, the Milky Way history is being uncovered. This found both in the halo and the bulge, and a little bit on the thick disk. There are ways to distinguish that are in situ. Pictures of accreted stars is the Gaia Enceladus sausage merger. That was the last major merger that happened with the Milky Way about 9.5 billion years ago. And the Gaia Enceladus sausage merger was discovered looking at these diagrams. This is the thumb diagram. Here you have the velocity in the disk of the galaxy. If it's positive, it's a prograde orbit. If it's negative, it's a retrograde orbit. And you can see that there is a feature here that people say that it looks like it's Gaia sausage. And this feature are composed mostly of accreted stars. But talking about the R process, the R process is responsible for the formation of these elements here in purple. So the bottom half of the periodic table. It's done going through a neutron-rich part of the chart of nuclides. In this chart, you can see here on the vertical axis the number of protons, here the number of neutrons. So each small square here is an isotope. And what happens to have is that a seed element, nickel or iron or another light element, receives tons of neutrons and goes into this path that is neutron-rich, and then decays until this line here in black, that is the line of stability. The source of the R process is still an ongoing debate on the literature. And the first time that we had an observational signature process was with the 0817, and it's, you can see here. You can see here this the dashed dots are the black body fit through the spectra, and this red line here is the black body plus the lines of strontium 2 on this transient. And you can see that the fissure of strontium 2 is clearly seen. Other elements was in this spectrum, like cerium and lanthanum, more recently tellurium, but it's still not a problem because there is a controversy in this spectra. Is needed a lanthanide-rich model. Others say it's a lanthanide poor model. Then when modeling the abundance in contribution in the Milky Way, people say, oh, 80% of the R process is done in events like this that are neutron star mergers. Others say, no, it's less than 20%. So it's a very hot debate on the literature. And what I'm going to show you on the following slides is an observational contribution to this discussion. There is a very recent paper from Patel and collaborators that proposed that on flares of magnetars, our process is done as well, but we don't know yet because nobody has done the contribution of the flares of magnetars to our process. So these neutron capture elements, there are two neutron capture processes that are generally the major contributor to the abundances of these elements. One is the slow that runs alongside the line and is mostly done on thermally pulsating AGB stars. And the rapid, that is the main focus of our talk, that are still in debate, but the best contenders are neutron star mergers and core collapse supernovae. We know that these dwarf galaxies that were gobbled by the Milky Way and that orbit the Milky Way, they are enriched in our process. The Gaia-Enceladus merger and another merger called the Sequoia was found to have an enrichment in our process that you can see here on the chart in the right. Here's the European over iron. European is the marker element for our process. And here is the metallicity. And you can see these stars here are from the Gaia-Enceladus merger, these black stars. And you can see that they have 0.6 more or less level in European. Guilherme Lindbergh published this paper in 2024 and about another dwarf galaxy, that the Milky Way, and proposed that in dwarf galaxies that are enriched with our process is mainly explained by the neutron star merger model. But we are going to talk about that a little bit more. So in my first paper, what I did was to use the Gala survey. The Gala is the Galactic Archaeology with Hermes. It's an Australian telescope. It provides 680,000 spectra for 480,000 stars in the data release stream. And it has up to 30 elements available for these stars. And at the time, it was the only one that provided large quantities of stars with European determined. So that's why I chose Gala to do this study. And then we integrate the orbits of the stars using the finest astrometry provided by Gaia in a Milky Way-like potential, going backwards 13 billion years. And of course, I did a Monte Carlo over the uncertainties to grab an idea of statistics. But to separate the stars in clusters, I used two unsupervised machine learning techniques. One of them is the T-distributed stochastic neighbor embedded. Here afterwards, TSNE, because it's a mouthful. For example, if you use PCA in this data sample, you can see that the clusters are not well defined. But with TSNE, the clusters are much more well defined. And it's an unsupervised machine learning application of the dimensionality reduction as the PCA. But it preserves the qualities of the neighborhood. So if one data point is next to another data point in an n-dimensional space, when it projects in 2 dimensions, they're going to be nearby. And that's the key of this unsupervised machine learning technique. So what we did was to get the best flags for this with metallicity below minus 0.8 in Gala. And then we use the dynamics and the chemistry, mainly metallicity and magnesium, that is an alpha element, to produce a TSNE match. Here is the sum for reference. And these colors here are groups. How we got these groups? We did a hierarchical agglometric clustering using Ward's method. This is super old in the literature. It groups nearby 2 points using Euclidean distances. And here you can see a dendrogram of this technique. In orange is the halo groups, and in green is disk-like groups. It doesn't have the sensitivity to separate the thick and thin disk because we are getting stars that are more metal poor than this separation. Here it's an example. I did this 50 times to get an statistics. And here is for the stars in the Gaia-Enceladus merger. So you can see here in the Lindbergh diagram, that one that I showed you first, the stars that I associate with the Gaia-Enceladus merger. And here on the action map, the stars that are associated with the Gaia-Enceladus merger. Here in this action map, it's really easy to see the stars that would be from the disk of the galaxy, because they are going to be located more or less here on the prograde, in the plane, and with circular orbits. here's a comparison of my stars with the literature. The sun is here for reference. So this is the halo plume. It's really nice that it separates in two wings, the halo and the disk. And here you have in green the Masari stars, the stars that are in agreement with the classification. The stars of Naidu 2021, of Fouillet 2023, of Lindbergh 2021, and mine. You can see that my classification is one of the most restrictive ones. Here are some results. Sorry for the Portuguese. What I did was to see how these groups behaved chemistry. And I chose 4 groups. So the Gaia Enceladus here in green, a prograde group, a little bit more prograde group than Gaia Enceladus, a little bit more retrograde, and the most retrograde group. I tried to see how they behave in chemistry. And you can see that conventional cuts in the kinematical spaces cannot reproduce well. So here is a Kiel diagram for the stars in Gaia Enceladus. You can see that they are very old, more or less 11 to 12 giga-years. And here is the metallicity distribution for Gaia Enceladus. We found out that the Gaia Enceladus has a metallicity of minus 1.23 with 35.35 spread. You can see that these stars for Gaia Enceladus are the most eccentric ones. This is in agreement with the literature. Most papers say that Gaia Enceladus can be found just by cutting here in 0.7 and getting the stars that are more eccentric. But you can see that in our case, it's stars that have eccentricity greater than 0.8. You can see here on the Tinsley-Wallenstein diagram that it's very difficult to distinguish from the background Gala sample only using magnesium and iron, but it has a low alpha. As it's in agreement with the literature, Gaia Enceladus has a lower alpha than expected. In general, you can have stars that have high alpha, but in general, it has lower alpha. And what we did was to separate using the magnesium over manganese and aluminum over iron diagram. So there is a line here that can distinguish accreted from in situ stars. So the stars that have black crosses over it, those are in situ contaminations. And you can see that this part here is the ex situ part. But to talk about their process that I was telling you, we can use europium and magnesium as the nucleosynthesis tracers for their process. So europium over magnesium we can think of as an rate of production of europium by magnesium, and metallicity as a proxy to age. If we see an increasing trend over metallicity, a source that produces more europium than magnesium, a delayed source like neutron star mergers, should fit better. And a flat trend is a quick source that produces europium in the same rate as magnesium, like supernovae type 2. So you can see here, in this is a figure from the paper of Skula-Dortir, 2020. And you can see here on this third panel that generally for the Milky Way, it's a flat trend. For Sculptor dwarf galaxy, is a flat trend. But for other dwarf galaxies are an increasing trend. And this is due to enrichment by neutron-star mergers, while on the Milky Way, core collapse supernova would be the preferred mechanism. And then I would like to see if my groups have the same behavior as the Milky Way, or it was enriched by neutron-star mergers. But you can see both Gaia Enceladus and my most retrograde group has a flat enrichment. So I'm obliged to conclude that this flat trend is due to core collapse supernova being the major contributor for Gaia Enceladus and this most retrograde group. We did also a Kolmogorov-Smirnov test to see if the groups were different in chemistry. And what we conclude is that just the most retrograde group and this Gaia Enceladus, the prograde, and the other that is a little bit retrograde are different in chemistry. All elements, only these 6 elements, they were different. So they have a difference in oxygen, in manganese, in yttrium, but not on the other elements available in the Gaia survey. So what are the main takeaways from? So this multi-dimensional chemodynamic analysis are useful to identify the substructure of the halo. There is a lot of contamination from in situ stars in all identified substructures. Some, like the most retrograde, the contamination was as high as 60%. The trend of European over magnesium in metallicity for accreted stars suggests the R process and magnesium is simultaneously by core collapse supernova. And no contributions from delayed sources such as neutron stars were observed in this metallicity range. If you have some doubt after our talk, I can show you a follow-up paper that I'm doing now, and there is a neutron star merger contribution for metallicity lower than the cut metallicity from Gaia. And chemically, there are 2 only dominant populations that comprise the accreted stars in Gaia. One is this population dominated by Gaia Enceladus sausage, and another one that can be associated with Sequoia or Tumnus that are other accreted galaxies in the history of our galaxy, but they are really smaller than Gaia Enceladus. So, having this technique of separating the groups, what I try to do is do some spectroscopic follow-up of some interesting stars to see if something rises up through attention. So what we did was to select our targets using barium, that is an S-process marker, and europium. So stars that had metallicities diverging too much, more than 3 sigma from the mean of the Gaia sample. And you can see here in red all the very metal poor stars that are stars that have metallicity below -2, and some interesting stars that have really high europium. The 2 of these stars that are colored differently here, to do a follow-up study, we sent a proposal to ESO. ESO approved the proposal. It was observed in P108 in February of 2022. We obtained 2 spectra for TIC. I'm going to only call TIC because it's a telephone number. And for the other star, I'm just going to say BPS. We obtained 3 spectra for BPS. It's high resolution spectra of around 41,000, and signal to noise of 2 line in 172 nanometers. And UVs have 2 principal arms. in the spectra. One is blue, that is centered in 390. The other one is red in 580. So I choose the to choose. And to get the atmospheric parameters, we use the calibration over the flux method. 2021. So these are one of the best methods to get effective temperatures for stars. To derive the surface gravity, we use Gaia parallaxes and to mass and Johnson bolometric corrections from Massana, 2006. And to get metallicity, we use iron 2 lines with the TS-FitPy wrapper. It's a turbo spectrum wrapper using the iron 2 lines from Melendez and Barbuy, 2009. Here is a sample of the spectra of the two stars. We did the kinematics after getting the metallicity and the magnesium. You can see that our BPS here is a more disk-like star, and TIC is in this prograde group that is associated with the Gaia Enceladus. Here is the TSNE map, same map that we had before. So here is a little bit more difficult to see the separation into the halo and disk, but it's around here. So you can see that TIC is here on this prograde group. BPS is here close to the sun. And these cyan stars are the stars in Saga database that have European over iron above 1.7. So it's highly enriched stars in our process. And you can see that there are some stars here alongside BPS, but there are SAMP stars and not, but BPS is not enriched in carbon. For you to see the lines, here's a Gaia benchmark star. Here is TIC, and here is BPS. And we calculated the European over iron abundance for this star to be to be 1.8, more or less. So it's a highly enriched star in European in the disk of our galaxy. It is about minus 2.46. And it was so enriched in our process elements that we could even do thorium. That is generally very difficult to do in spectra of stars. So here you have the thorium 2 line, and it's well fitted. Here on this plot you can see the of our process enrichment. R1 is generally said that are stars that have enrichment in European above 0.3. Above 1 are the R2 stars, and there is a proposed category that's called R3, but there are just very few stars on this classification. So you can see that BPS that was a star that we serendipitously found on the Gala catalog and did the spectroscopic follow-up. It is very enriched in our process, indeed. And our other star, that is TIC, has a level of European above 0.5 that is in agreement with our merger. So here you have stars that have been associated with the Gaia Enceladus merger. And here you can see TIC kind of fits this magnesium 4 part of the stars that have been associated to the Gaia Enceladus. Here is a comparison of our process pattern from BPS and TIC against the solar our process pattern. you can see that for some elements it doesn't fit well. So what we did was to try to fit model of population tree and neutron star mergers to these stars to see what are the probable progenitors for these two stars. So here we fitted using StarFit all the measured abundances for BPS. And you can see that it has this beautiful even-odd effect that is characteristic of population tree supernovae, and it fits well with a model of neutron star mergers. There are some elements here that are on excess from the model, but this is fission fragments. And in the paper, we discuss how it. So if you have doubts about it, you ask me or you go to the paper to see. We did the same for tick, and you can see that the same population, not the same, but again, a population tree model and neutron star merger event best fits the abundances that we find in these two stars. You can see here the models going up and down. So what are the main takeaways from this paper? We managed to get for BPS 47 chemical species, 44 elements, including 27 neutron capture elements with 15 non-LTE corrections. This is the most chemical element determination done for a star, for a metal pulsar. BPS is an R2 non-SAMP star with disk-like dynamics, with mono-enriched in population tree supernova. Antique is an archetypical R1 star from Gaia Cellular Sausage merger. Just a brief presentation about what I was doing the last year and probably what I'm going to do on the following years. We did a follow-up of some X plus stars using SALT. SALT is a South African large telescope. So I guess I don't need to rely much in explaining what S plus is, because I think you are exposed a lot to S plus, but S plus is a photometric survey using a robotic telescope on T8 South in Cerro Tololo. It has 12 filters. Some are narrowband and some are broadband, from the ultraviolet to the infrared. I guess this number is unupdated, but at the time it covered more than 8,000 square degrees of the sky. And what we did was to select 23 stars and observe with SALT with this resolution and signal to noise, and see if there were metal pulsars indeed. We try to do the same analysis as well. There are some stars that could be from the most retrograde group, but more study is needed. Here you have a Q diagram for these stars from S plus. They are red giants. They are enriched in magnesium, but most of all, they are very metal poor. So we found from that 28, there are 7 stars that are 3 is extremely metal poor with metallicity below -3, and 4 is very metal poor with metallicity below -2. But unfortunately, the SALT spectra for this observation was affected because SALT had a problem with this guiding system. So the spectra was not great to do the neutron star capture elements. But again, S plus is a gold mine for this kind of stars. There have been 3 or 4 papers in the literature using S plus to find metal poor stars. And further follow-ups with high resolution and signal to noise are needed to determine this neutron capture elemental abundances. That's all for today. Muito obrigado.
Muito obrigado, André. Temos perguntas?
Pode fazer a pergunta em português, tá? Não tem problema, não.
Aqui todo mundo craque em inglês.
Hello, thank you so much for your lecture. I have a very specific question about the algorithm. I think is the stochastic neighbor embedding. I was wondering if first you need to take, you do yourself the PCA, and then in that projection you apply the clustering, or is it if it's all together within the TensorFlow pipeline, and then the own algorithm does for you all the projections and clustering given your dimension?
Let me explain better then.
Okay.
So PCA is one dimensionality reduction tool that we can use. TSNE is another. You can initialize TSNE if you want, but it's not necessary, and it's not our case. So the initialization of the TSNE here, for me, use a randomic initialization. But you can use a PCA as well. And the clusters, they are done with using the Ward's method. So what I did was to do 50 times the TSNE with this randomic initialization, and then 50 times the hierarchical clustering with the Ward's method. So to get some idea of the statistics, this is very computationally intensive. So it took a while.
Alguém mais?
Did you check for uranium in the star that is enhancing their process?
Which one?
Uranium.
I checked. The lines are there, but the resolution was not enough. Because here I'm using 41,000 of resolution. For you to determine uranium, you will need to have 50,000 at least. There is a paper from Shah and collaborators, 2023, and she shows that from 50,000 resolution up, you can do uranium. But the lines are there. They are visible. But you cannot do the abundances because it's blended with some other lines.
In the first part of your talk, because the spectroscopy analysis, you ended up with this smaller number of merging neutron star events, as you know, and is this kind of expected or not? I'm saying so because these events are expected to be more rare, right?
Yes.
And
it's expected to.
Exactly.
Here you say, right?
Before, because in the first part of your yes, and then you got that okay, you
here.
No, I think it was before the.
Oh, it was for the start.
Yeah, exactly. You
here.
Yeah, exactly.
Okay.
And then, but then in the spectroscopic analysis, you got kind of the same, right? So isn't that kind expected because merging neutrons are more rare?
Yes, it's somewhat expected because neutron star mergers are rare events. But here, the trend doesn't agree with neutron star mergers.
Mm. Mhm.
So there is a conundrum.
Right.
So in the spectra of stars, the best fitting model was neutron star merger,
Mhm.
but on general, on the population,
When you do population studies, you
it's
don't
not.
get so. Mhm.
So, but this is for a big merger
Mm.
of the Milky Way. The Gaia Enceladus was the or less major merger.
Mm.
So there is still a debate on the community. I don't know the answer why
Mhm.
this happened. Maybe it's because you see here that in Gala the metallicity only goes around -2, a little bit below, and those stars are -2.3, -2.46. So maybe there is a regime that the neutron star mergers were really important in the early times, and then the core collapse supernova took
Mm.
the
Ah.
the major contribution, and then what we are seeing is after the knee
Right. Right.
in the plot.
Yeah, makes
So-
sense. So a historical, let's say, a cosmic
Yes. So as
evolution.
there is a change from supernova type 2 to supernova type 1
Mm.
in the Tinsley-Wallenstein diagram,
Mhm.
and you see a knee,
Mm.
maybe here we have a knee as well.
Right.
And I'm preparing a paper showing the knee. So there is a
Uh-huh.
knee there. I already know there is a knee there.
Okay.
But it's still controversial in the literature.
Right.
Because for this really R process enriched, maybe only neutron star mergers can produce this kind of enrichment.
Right. Mm.
And then because there is not enough mixing in the clump or some other process, these stars can have europium really high.
Mm.
And when mixing and diluting takes place, you can see this
This
flat
behavior.
trend.
Mhm.
So this is an explanation. I don't know if
Mhm.
it's what is actually happening.
Okay, but interesting, anyways. Yeah. Thanks. Thanks for the answer.
Are you also interested in considering these stars in the history of accretion in the galaxy?
So these stars here,
I know they are. You can study metapore stars just by them. They are very interested, and they can give us many signs of the different origins that they have. But are you also interested in seeing the history of accretion
yes,
by studying these stars?
yes. You see here,
Ah.
on this plot, we have these green stars that are from Gaia Enceladus.
Uh-huh.
And what I'm saying here is that this flat trend is observed in Gaia Enceladus.
Okay.
And you see this black crosses? These are the in situ contamination. So we can divide it, what is accreted, the green stars here, and what is in situ, the black crosses.
Okay. And when you were selecting stars from S+, do you take that into account?
No, because I couldn't do
I imagine that.
aluminium and manganese because the spectra was not nice. But if I get more spectra, and
Yeah,
It's
and the
really not
statistics is another interesting point because we know that the more metal poor they are, the rarer they are. So we need more.
yes, we need more. And by the way, this star, the DPS, it's the only star with this metallicity range, like -2.46, with an R process enrichment of R2 level 1.8 in the disk of the galaxy. That is not carbon enriched, because you can see carbon enriched stars
Yes.
in all substructures of the galaxy, and they can present R process or S process enrichment. But this star is not carbon enrichment. So the
Yeah,
carbon of
that's
iron
cool.
is like 0. So
Yeah.
it's really nice to see such rare star
Mm-hmm.
in our sample.
It is. More questions? Sorry, I just asked mine and nobody else? Okay, let's thank André again. Thank you very much.
Thank you.